Good day, everyone, and welcome to the Canadian Math Kangaroo Contest Mini Enrichment class, this time on strategy problems for grade 5. Today we will be learning about strategy problems that don't have a ready-made algorithm or procedure to solve them. These problems might require us to come up with a specific strategy, and this strategy in most cases will be informed by what we see in the problem itself. We'll be doing a little bit of creative work today, I think. We will also illustrate the process of creating these strategies. We will try wherever possible to make a strategy generalizable. That is, one that might help you in the future should you encounter a similar problem up ahead. Let's jump straight in and get started. Suppose Basil is encrypting or ciphering numbers using the following rules. He increases each even digit by 1 and decreases each odd digit by 1. So for example, the number 4891 is to be replaced by 5980 after Basil has ciphered it. 4 and 8, being even digits, will be increased by 1 into 5 and 9, and 9 and 1 will be decreased by 1 into 8 and 0. Similarly, the number 1342 will become 253 after Basil has finished ciphering. 1342 turning into 0253. After ciphering a 4-digit number that is divisible by 3, Basil also got a number that is divisible by 3. How many even digits do you think there were in the initial number? Take a minute now, pause the video, try this system of Basil's on some numbers that you can come up with. Make sure you get the hang of the problem, and then try and come up with a strategy for how we could solve this. Again, there are a lot of 4-digit numbers. We don't want to be going through all of them. Are you ready? There are a lot of things to remark here, but mostly we have a 4-digit number that's divisible by 3, and after the transformation it will still be divisible by 3. So since we don't know what 4-digit number there is, and as previously mentioned there are a lot of them, let's label it as ABCD, where each letter stands for 1 digit and A is not the 0 digit. Thus we will have a 4-digit number. Somehow we also want to encode that this number is divisible by 3 so that I don't have to say divisible by 3 each time. We can of course say something like, well, it will have a remainder of 0 when we divide it by 3. That's what divisible by 3 means. But it isn't all that general and it doesn't really help us with our abstract ABCD. How else can we describe divisibility? We can rely on our divisibility rules, of course. If a number is divisible by 3, the sum of its digits must be divisible by 3. As a slight aside, this also works for 9. If you have the sum of digits of a big number be divisible by 9, that means the number itself is divisible by 9. There are different, distinct rules for other digits, but we're getting ahead of ourselves. For this problem, we just have to remember that the sum, a plus b plus c plus d, must be a multiple of 3, must be divisible by 3. Well, that's still a lot of 4-digit numbers out there, so we will probably have to study some cases, right? We might have the 4-digit number have some mixture of even and odd digits in it, perhaps all even or perhaps all odd. Is this possible? Let's take a look. Suppose that all the digits are even. In that case, our system tells us that we must increase each even digit by 1. That would mean that we would increase the sum by 1 plus 1 plus 1 plus 1, increasing the sum by 4. Can we take a number that's divisible by 3, increase it by 4, and still have the result be divisible by 3? I'm afraid not. We would be adding a remainder of 1 to our divisibility. That's no good. Similar idea if all the digits are odd. Were Basil to cipher the number that is 4 odd digits, he would be subtracting 1 from each digit, which means that for our sum, a plus b plus c plus d, originally divisible by 3, under the transformation would become a minus 1 plus b minus 1 plus c minus 1 plus d minus 1, aka the sum minus 4. And because there's a change of 4 again, we cannot have the result of the transformation still have a sum that's divisible by 3. So no, we cannot have a number that is all even digits or all odd digits. Let's study more cases. Can 3 of the digits be even? What would that look like? 4-digit number, 3 even digits, that means 1 odd digit. We are increasing each even digit by 1, decreasing each odd digit by 1. So the sum would increase by 3, 1 for each even digit, but decrease by 1 for our odd digit. The resultant sum would be increasing by 2. Again, we can't take a number that's a multiple of 3, a plus b plus c plus d, add 2 to it or subtract 2 from it, and still have the result be divisible by 3. So no, this is not possible. Can 2 of the digits be even? What would that look like? 2 even digits, 2 odd digit. Each even digit increases by 1. So we're increasing by 2, but we're also decreasing by 2, 1 for each odd digit. Overall, the sum won't change. This is a distinct possibility. We might have a plus b plus c plus d divisible by 3, and after our weird transformation, some digits increase, some digits decrease, but the sum total doesn't change, so it's still divisible by 3. Can one of the digits be even? That would make the other 3 digits odd, and we run into the same case of an overall change by 2 that we've discussed before. Not possible. So we have found, without testing a whole bunch of cases, hopefully, without spending too much time on this problem, without thinking of all the possible 4-digit combinations that there could be and all the transformations that happen, we have identified the one possibility that exists. The 4-digit number that we consider must have 2 even digits and 2 odd digits, and it must be divisible by 3, in which case, after the transformation, the resultant number will also be divisible by 3. Problem solved. Let's try another one. Let's consider writing the numbers from 1 to 13 into this figure right here, the circles of the figure, so that we have the same sum for the 4 numbers on each connected side. So there is going to be the same sum along any of the slanted lines, the same sum along any of the horizontal lines. What number should go in the place of A, right at the top of the figure? Again, please take a minute now, pause the video, solve along, try some things, figure out what strategy we might work towards. Are we ready? Often I find it useful asking myself what it is about the problem that makes it so difficult. Sometimes in the face of a difficult problem, that can actually be therapeutic and helpful. Here, this seems like an intractable problem. There's 13 different numbers floating around. We can move them around the page however much. We need the same sum. What can I identify as being hard that I do have some control over so as to make it easier? For me, I find it very restrictive that we have the same sum along many different lines, 4 slanted lines and 3 horizontal lines. Well, I don't even know what the sum is that we're looking for. Perhaps that could be something that I could actually figure out. Let's try it. I'm going to consider this 1 to 13 business in 2 different ways. First, I'm going to think of the oblong lines. Those would be the slanted lines that I've colored in, right? So I have the same sum along the 4 circles, the 4 orange circles that you see there, including the circle A at the very top. And the same sum comes from adding up all the green circles, including A. And the same sum comes from adding all the blue, including A, all the purple, including A. What's another way of looking at this sum, though? Because all of those circles are just the numbers 1 to 13 in some fashion and some shuffling. What happens if we add all the colors together? Again, as I mentioned, what's making this problem very difficult is not knowing the sum. So I'm going to give this sum a letter. I'm going to call it big S for the sum along one color. So there, looking at this picture now, I know that adding up all of the slanted line sums, I should have 4S in total. S on the orange, S on the green, S on the blue, S on the purple. 4s in total. But thought of it another way, these are just the numbers 1 to 13. However, I am counting the top number 4 times, not just once, right? Every other circle appears in the sum just once, but the number a will appear 4 times. So if I want to think about this, this is the sum of all the numbers 1 to 13 and the 3 other repeats of the number a, so that I would repeat a 4 times in total. This is the beginning of something good, right? I think 4s equals all the number sums plus 3 times a. I can think of the horizontal version of this as well. I can look at the 3 horizontal lines, those are 3s, and then the a at the very top, and that together will total 1 plus 2 plus 3 plus 4 plus 5, all the way up to plus 13. We've mentioned already identifying something that is difficult and making it a little bit less so. I keep saying 1 plus 2 plus 3 all the way to 13 when I'm just being lazy. We can probably figure this out. What would 1 plus 2 plus 3 plus so on plus 13 equal? Let's see. It would mean I have 1 plus 13, that's 14, 2 plus 12, that's another 14, 3 plus 11, that's another 14, and so on. Maybe you even know a shortcut formula for this. The total sum will be 91. Great, I've learned a lot. Thought one way, this figure has 4s being equal to, along all the slanted lines, 91 plus 3a. Thought another way, this figure is 3s plus a equaling 91. In fact, I can isolate for a in that second equation, a equals 91 minus 3s, and I can plug it into the first one because now I have a system with 2 unknowns, 2 equations. It is definitely solvable. So let's replace a in the first equation by what we know it to be, 91 minus 3s. 4s equals 91 plus 3 times 91 minus 3s. Careful expanding those brackets. This is going to be 4s equals 91 plus 3 times 91 minus 9s. Moving the s's to the other side, this is 13s equals, no need to torture ourselves with arithmetic. We have a 91 plus 3 times 91, so we have 4 times 91. Why did I not multiply that out, other than to not make my life difficult? Because I recognize that 91 is a special number. It is divisible by 13. Looks like prime, but it isn't. It's 13 times 7. Knowing that, I can very quickly see that s would just be 4 times 91 over 13, 4 times 7, 28. Excellent. It's not what we were asked to find, but it is a huge step forward. Now we know that the sum of any of those 4 numbers along any of those connected lines is just 28. And in fact, the problem falls away quite quickly because we already, in trying to figure out s, have a bunch of formulas that are useful. You can see them in the highlighted yellow there. A is 91 minus 3 times s. 91 minus 3 times 28, a must be 7. After we have figured out the difficult part, the part we were actually asked for is just a one-line derivation. We have figured it out quite quickly. Let's try another problem. We write numbers on empty pieces of paper. One we write on each piece of paper. So for example, we write the number 1 on one piece of paper. We take 2 scraps of paper and write 2 on each of those. We take 3 pieces of paper and write 3 on each of those, and so on until we write 10 times once on each piece of paper. We mix all these papers up and we draw randomly from them without replacement. At least how many papers should we draw to be sure that we have 6 identical numbers? Please pause this video now and try and solve along, figure out what this looks like, maybe draw yourself a picture or a table, and then figure out what strategy you might use to approach this. Good luck. Let's see what we can glean from this problem. Again, we are asked for a guaranteed 6 identical numbers in our hand. We can once more ask ourselves, what are some things that are currently difficult that don't have to be. For example, we don't even know how many pieces of paper we have in total, but that is something that we can very quickly figure out. One piece of paper with one on it, two pieces of paper with two, three pieces of paper with three, all the way to 10 pieces of paper with 10, 1 plus 2 plus 3, all the way up to plus 10, 55 pieces of paper. So whatever our guaranteed 6 identical numbers in the hand number is, at most it is 55, and it is probably less. In solving this, we actually have a good headway into seeing what another problem might be for us. If we want 6 identical numbers in the hand, and we're hoping to get 6 identical threes, for example, that's never going to happen. There are only 3 threes in that entire pile, only 2 twos, only 1 1. So now, because we want the least number that will result in a guarantee, we are going to be looking at the most unlucky person that we could be in the world. Let's imagine the unluckiest person in the world. They will take the longest to get their 6 identical numbers. First thing they might do is they might, through their unluckiness, pick out the number 1 and the numbers 3 and the numbers 2 and all the pieces of paper with a 4 in them and all the pieces of paper with a 5 in them. They can't ever hope to complete 6 identical numbers in the hand of any of those. So how many papers must they have taken out? They must have taken out 1 plus 2 plus 3 plus 4 plus 5. After that, after they've done that, now they have some hope, right, of having 6 identical ones. Only from 6, 7, 8, 9, or 10. So how many papers have they taken out by this point? 1 plus 2 plus 3 plus 4 plus 5, 15 pieces of paper. Great, 15 pieces of paper already taken out of the pile by the unluckiest people in the world. Now, how many do they still take out, continuing to be super unlucky, before they have 6 identical numbers? Now they're working with just the digits 6, 7, 8, 9, and 10, and theoretically, they could have 6 of any of those. But what happens if they're very unlucky? Well, they're going to take 5 of each of them. 5 sixes, and then 5 sevens, and 5 eights, and 5 nines, and 5 tens. Still no completed set of 6, you'll notice. But this is maximum unluckiness at this point, right? So how many papers is that? 5 times 1, 2, 3, 4, 5 possible digits, 25 pieces of paper extra. By this point, they've already taken 40 pieces of paper out of this pile of 55, and still they have 1 1, 2 twos, 3 threes, 4 fours, 5 fives, 5 sixes, 5 sevens, 5 eights, 5 nines, and 5 tens. Talk about unlucky. But what happens on the next step? On the next step, they reach into a pile of papers that has 6, 7, 8, 9, and 10 in it. No matter which number they take out, they will be adding to a set where they already have 5. They will be drawing their 6th identical number. Hooray! So they will complete the set on the next draw, which means in total they must have drawn 15 plus 25 plus 1, 41 papers, and we are guaranteed to have 6 identical numbers in our hand. If you're interested in these types of problems, I encourage you to look into pigeonhole principle style problems. You'll see this kind of strategy appear there all the time. This was quite a big problem, wasn't it? One of the things that might be interesting to consider is how the problem would change if we only required 5 identical numbers instead. Try that out when you have a minute, just for fun. Another question. There is a magic tree in the orchard. It bears both bananas and oranges. Right now, it has 25 bananas and 30 oranges. If we collect 2 fruits of the same kind from the tree, an orange will grow back. If we collect 2 different fruits, then a banana will grow back. What is the last fruit that one would collect from the tree? Take a minute now, work out what we're doing. 25 bananas and 30 oranges on a tree. Collect 2 oranges or 2 bananas at a time and an orange will grow back. Connect a banana and an orange and a banana will grow back. What is the last fruit on? Whenever I see a problem that specifies some rules based on how some things might happen, I think it's very important for me to understand how the rules work, to spell it out on a page somewhere so that I know I don't make a mistake. That way, I might actually see a little bonus. I might see not only how the rules work, but how they apply to a particular situation that might even spark something of a solution for me. So here's what I know. I know that if I collect a banana and a banana, I get an orange back from the mutant tree. If I collect an orange an orange will grow back from the mutant tree, and orange and banana will result in a banana. This is a strange tree, but it's very mathematical. One thing that I'm noticing is that the total number of fruits is going to decrease by 1. I'm always collecting 2 fruits and having 1 grow back. So it does actually make sense to ask what the last fruit will be. This mutant tree will not continuously grow fruits until I can no longer defeat it, like some sort of Hydra monster from Greek mythology. No, the fruits are decreasing. Another thing that I'm noticing is that I'm always collecting 2 fruits and getting 1 back, and the fruits are bananas and oranges, so I might want to focus on what happens with the bananas and what happens with the oranges separately. For example, the bananas on any turn might decrease by 2 or remain unchanged. What do I mean by that? I collect 2 bananas and get an orange. That's 2 less bananas on the tree. I collect a bunch of oranges and get back an orange. Nothing happens to the bananas. I collect an orange and a banana grows back. Nothing changes to the number of bananas on the tree. So considering my 3 scenarios, they are decreased by 2 in the bananas, unchanged bananas, unchanged bananas. How about oranges? Those can either decrease by 1 or increase by 1. In the first scenario, where an orange grows back from 2 bananas, we are increasing the orange count by 1. In the second case, where 2 oranges are picked but 1 grows back, we are decreasing by 1. And in the third case, an orange and a banana are picked and a banana grows back. Again, a decrease by 1 happens. So the number of bananas will decrease by 2. The number of oranges might increase or decrease by 1 depending. But I only had 25 bananas to begin with. What happens if I keep taking away multiples of 2 from an odd number? Eventually, I'm going to be left with 1, right? An odd number minus 2 times x for whatever x will result in an odd number in the end. So the last fruit must be a banana. I don't know the mechanics of this tree. I don't know what's going to happen. I don't know how long it will take. I know that eventually the process will terminate. We will have only 1 fruit left because the number of fruits keep decreasing. And I know that because I started with 25 and I keep either keeping 25 as is or decreasing by 2 each step, I must in the end have just 1 banana. There are a number of problems that might appeal to you that have a similar idea, where we have rules, a certain amount of decreasing, a certain amount of increasing. In fact, I encourage you to come up with a problem of your own and inflict it upon your friends. They're quite fun to do in the end. Well, it's very fitting that I mentioned the Greek Hydra monster in the previous problem, because here's another one. A prince wants to cut the heads of 100-headed dragons. He can cut 9, 10, or 11 heads with one swing of the sword. However, there will immediately grow back 6, 13, or 5 heads respectively. What do we mean? If I cut off 9 heads, 6 will grow back. If he cuts off 10 heads, 13 will grow back. If he cuts off 11 heads, 5 will grow back. If all the heads are swung off with one swing, the dragon will die. Can the dragon ever die? Again, please pause the video, consider the problem on your own, and then come back for a solution. Ready? This is quite similar to the previous problem, isn't it? There is once again a rule. Some things are increasing or decreasing. And there is a starting off point. There's 100 heads. Now there are quite a few rules, 3 that I can see, so I'm going to synthesize them into a table. Again, 9 heads to begin with results in 6 heads, a decrease of 3. 10 to 13, an increase of 3. 11 to 5, a decrease of 6. I'm noticing something right away in my table. I'm noticing that the change is always a multiple of 3. And so the only way I hope to defeat the dragon is to eventually get to a point where the dragon only has 9 heads, or 10 heads, or 11 heads. In that case, the prince will be able to take one swing of the sword, cut off all the heads, and then they won't be able to grow back. Awesome. So what do we know? We know we started with 100, and we know each step we're either taking 3 less, 6 less, or 3 more. So we are using multiples of 3 to eventually get ourselves down to either 9 heads, or 10 heads, or 11 heads. Is this possible? Well, let's consider 100. 100 is not a multiple of 3. It is one more than a multiple of 3. And so if we keep taking multiples of 3 away from it, or adding multiples of 3 to it, we're still going to have a remainder 1 when divided by 3. So is any of the numbers 9, 10, or 11 one more than a multiple of 3? Yes, 10 is. So it must be true that we could remain with 10 heads in the end, and then one swing will finish off. Can we get to 10 heads from 100? Indeed, we can. We can cut off 9 heads at a time 30 different times. Every time we would make 3 less heads. This is only one solution. You could, of course, start, adding more heads if you feel like it and then coming back. But the easiest thing to do, cut off 9 heads at a time 30 times, making 90 less heads after the 30 swings, and then the final 31st swing, we cut off all 10 heads at once and the dragon dies. We as mathematicians have vanquished the problem, and the prince is free to consider whether he wants to vanquish the dragon or not. Perhaps a 100-headed dragon is cool just to keep as a pet, as long as you know how to defeat him. So yes, the dragon can die. How about this problem? A 256 by 256 grid is filled with the numbers -1, 0, and 1 in each square. Then we calculate the sum along each row, each column, and on the 2 main diagonals. Is it possible that all 514 sums, that is 256 row sums, 256 column sums, one cross diagonal and another cross diagonal, all of those are different? Take a second now and work it out. We have here another problem that is a yes or no answer. If the answer is yes, we're stuck showing a procedure for how this might work, which is probably going to be long and tedious. If the answer is no, all we need is a simple argument for why such a procedure is never possible at all, and we would be done with the problem. Are you ready for us to take it up together? I don't know about you, but I find 256 by 256 entirely too big of a grid to think about. So instead, I'm going to think about smaller numbers. If I find something that works, a solution for a 4 by 4, for example, it might give me a better idea for what to do in my more giant case. So if I consider a 4 by 4 grid, that's 4 row sums, 4 column sums, 2 diagonals, 4 plus 4 plus 2, 10 sums in total to consider. That's a lot easier on my brain than 514. We can, of course, play out some different configurations and see if we can get to a point where we can make a verdict. Is it going to be possible to have different sums all around, or are always 2 sums guaranteed to be the same? Still quite a lot of numbers to consider, isn't it? So I'm going to do another trick. I'm going to try and figure out what the maximum and the minimum sums might be, just to know how far I can reach. For example, I can put -1 into each cell along a row, and that will be the smallest sum that I could have. -1 plus -1 plus -1 plus -1 giving me -4. I can't achieve a sum smaller than that in any row, column, or diagonal if I'm only using the numbers -1, 0, and 1. Similarly, I can consider what happens if I want to put a bunch of +1s in a row to give myself a row of +4. That would be the biggest sum that I can achieve. And indeed, as you can see in that other diagram here, I would be looking at something like 1 + 1 + 1 - 1, a total of 2, in my first column, for example. And in fact, anything, because I'm allowed to use zeros, any number between -4 and 4 is achievable as a row sum, or a column sum, or a diagonal sum, somewhere in here. Well, what does that mean? I can achieve a sum of -4, -3, -2, -1, 0, 1, 2, 3, or 4. That's 9 different sums that are possible for me. But I have 10 sums in all. So again, it's looking like I'm going to have a repeat of the sums, right? 9 sums that I can get. Again, all of these are achievable. Just replace some of the ones by a 0 or by a -1. But I need 10 distinct sums. So it's looking like the answer might be no, even in my enormous giant case. Let's see what we can get up to. 256. Well, the smallest sum is -256, just like it was -4 before. The biggest sum is +256. And we've already said there are 514 sums in total. How many possible sums can there be? -256, -255, -254, all the way up to -1, 0, 1, all the way up to +255, +256. Let's see. 256 on one side of 0, 256 on another side of 0, and the 0 sum itself. That gives me 513 different sums. But 514 sums in total, so one of the sums at least must be the same as a different sum. Therefore, no, it is not possible to have all 514 sums be different. That's it. We have solved through quite a few difficult problems today. These were presented in particular contexts, but hopefully you have seen that many of them have some similarity to their structure. We have seen cases where we relied on parity or divisibility, odds and evens and rules of divisibility. We've seen a problem where we really needed to break things up into cases. We answered a problem based on trying a downsized version, one that was smaller and easier to manage. All those elements are going to be important ingredients in all of your problem solving now and well into university. Thank you very much for listening, and hope that you will take pleasure in solving many different word problems from now on. Bye.